Hello! In this presentation, we will be talking about the use of supercritical fluids for the extraction of cannabinoids. My name is Eyram, and I worked with Ruby, Natalie, and Kim for our project.
Here is our motivation for choosing this topic. One of the earlier uses of supercritical fluid extraction, or SFE, was to make decaf coffee by separating the caffeine from the rest of the coffee bean. SFE is also used for extracting oils, removing plant fibers, and extracting cannabinoids. Cannabinoids are very useful for treating health problems. For example, Epidiolex, a drug used to treat severe epilepsy, contains purified CBD. The hemp plant's cannabinoids are mostly used for their oils or pharmaceuticals, but hemp is also being used for other industries, such as plastics, paper, and textiles. It is projected to grow by 34% from $4.6 billion in 2019 to $26.6 billion in 2025. As the industry grows, coming up with new uses for hemp and more refined ways of extraction will be highly beneficial. SFE is the use of supercritical fluids to extract compounds from biomaterials. It is considered a green and safe process. CO2 is considered greener because it is easily removed from the system, and although it is a greenhouse gas, it leaves no trace once evaporated. CO2 is also considered safe because it is inert, non-toxic, non-flammable, and it won't leave any residues behind, unlike organic solvents. SFE is also the most economically viable. Since the CO2 is evaporated at the end and is free of organic compounds, it leaves the user with a high extraction yield. Although it is more expensive compared to other extraction methods, it has the highest profit due to the high purity of the product. At a supercritical state, CO2 has properties of both a liquid and gas. CO2 becomes supercritical when it reaches a critical temperature and pressure of around 31 degrees Celsius and 7.4 megapascals. For example, it has a high density like a liquid and a high diffusivity like a gas. CO2 is very popular as a supercritical solvent because of these properties.
Let's take a look at the overall process. So the schematic, which will be fully revealed by the time I'm done talking, clearly shows the key components of the supercritical fluid extraction of hemp. In the process diagram, CO2 passes through a cooler to reduce its temperature, bringing the gas to a liquid state. And in this state, the CO2 can more easily go through the pump. In the study where the schematic comes from, the researchers used a co-solvent, ethanol, which is mixed with the CO2 in the mixer. However, for the simplicity of our calculations, we decided to not consider the effects of the co-solvent, which is why that part of the diagram is crossed out. The liquid CO2 is heated to its supercritical state using an electric heat exchanger, which for our purposes, we consider to be a shell and tube heat exchanger. The supercritical CO2 then enters the extraction vessel, and once the vessel reaches the desired pressure, the automatic back pressure regulator opens, which allows the supercritical CO2 and the compound soluble in it to flow through the extractor. From the extraction vessel, the solution flows into each of the separation containers, which are all set to different temperatures and pressures in order to achieve the proper precipitation of the solubilized compounds. The extracts can be collected from each cylinder by opening the drain valve.
So we know that the driving forces for both heat and mass transfer are a temperature and concentration gradient respectively. So something we wanted to figure out was how we determine a somewhat accurate measurement of these qualities using the information that's available to us. So one way that we can determine those things is through the calculation of the diffusion and overall heat transfer coefficients, which is the basis for our analysis, since they illustrate the proportionality of flux to driving force gradient. So in general, for the determination of energy usage in a heat exchanger, via calculation, assumption, or through estimation, also as well as using a couple of equations for the heat duty, you have to account for the heat duty itself, the driving force of the heat exchanger, which is the log mean temperature difference, the specifications or dimensions of the system, in this case being the surface area, as well as the overall heat transfer coefficient, which is our unknown. So like I stated previously, we had to make some assumptions in order to begin our calculations. Firstly, the specifications of our system were based on some preliminary studies completed by Rovetto and Ayeda in 2017 on the extraction of cannabis oil. Additionally, we assumed that our heat exchanger was adiabatic, meaning there's no loss of heat to the surroundings. We also assumed that the heat exchanger itself was a countercurrent single pass heat shell and tube heat exchanger, with the shell side fluid being water and the tube side fluid being CO2. 3 of the 4 temperatures needed to calculate the log mean temperature difference were already outlined in the study previously completed, but the outlet temperature of water was calculated using that equation for heat duty. Additionally, the mass flow rate of CO2 and the mass flow rate of water we assumed to be equivalent, which is 0.2 kilograms per second. And then lastly, for the heat capacity of CO2, since it's achieving a supercritical state where the phase boundary is non-existent, we had to make an estimation using the arithmetic mean of the CO2 heat capacity of 2 different temperatures, which we acknowledge is not the most accurate, but was sufficient for making some kind of calculation. So in the end, we were able to find a value for all 4 of the unknowns for our heat exchanger. For the heat duty, we found it to be 8.788 kilojoules per second. The driving force, or the log mean temperature difference, was 52.68 Kelvin. For the surface area of the system, we assumed a surface area of 1 meter squared to get an overall heat transfer coefficient that is on a per meter squared basis. And then lastly, the final figure for our overall heat transfer coefficient was 0.1573 watts per meter squared Kelvin.
After the carbon dioxide goes through the preheater, it enters into the extraction vessel as a supercritical fluid. Using data obtained from research articles, we were able to describe the mass transfer of the cannabinoid extracts into the supercritical CO2. To begin, we took a look at fixed flux law and made a few assumptions to simplify the equation. We assumed that only diffusive flux occurred. We used a cylindrical coordinate system, and we said that only one-dimensional mass transfer occurred and that it would be in the z direction. We also had to make a few assumptions regarding the physical system. In the article, the vessel had a volume of 5 liters, but the dimensions were not included. Therefore, we assumed that the vessel had a height of 0.8 meters, which corresponds to a diameter of 0.09 meters. Additional assumptions include that there was no change in the volumetric flow rate and that the system was isothermal. We also retrieved data from the article by Rovetto and Ayeda. The table below contains important information from their work that we will be using in later calculations. All of the concentrations are given as mass percents, and the cannabinoid mass percent is a sum of the THC, THCA, and CBD percents. We also calculated the molar weights of the different extracts and found the mass flow rate from the article. Using these values, we were able to determine the final concentration of THC in the CO2, the diffusion coefficient, and the flux of THC from the system, as well as the cross-sectional area of the vessel. For the final concentration, we found that it would be equal to the density of the supercritical CO2 times the solubility of the cannabinoid extracts in the CO2 times the THC to cannabinoid mass ratio, and that it would all be divided by the molar weight of THC. For the cross-sectional area of the vessel, we used the assumed diameter to within the area equation here. And then for the THC flux, we found that it would be equal to the mass flow rate of the CO2 times the solubility of the cannabinoid extracts in the CO2 times the mass ratio divided by the molar weight of THC divided by the area. Perhaps the most important of the mass transfer calculations was the diffusion coefficient determination. We had to make one more assumption that the initial concentration of the THC in CO2 would be equal to 0. Starting with the simplified fixed flux law, we integrated the equation and then solved for the diffusion coefficient and found that it would be equal to the flux of THC times the difference in height, all divided by the final concentration of THC in the system. Using these calculations, we were able to determine that there was an increase in the final concentration, the flux, and the diffusion coefficient as the pressure of the system increased. And it's likely that this occurred because the THC molecule is more stable than its acidic counterpart, considering that the THCA molecule has a carboxylic acid group. And as the heat increases, or in this case, as the pressure increases, it destabilizes that part of the molecule.
So overall, we found that using the scenario of using supercritical fluid for the extraction of compounds provided a good basis for us to display what we know. It allowed us to decide what information was necessary, and it gave us a view into making reasonable assumptions, as engineers often have to do in order to find a result. And additionally, it gave us ample opportunity for inferences to be made regarding both heat and mass transfer. As well, we were able to determine key values in addition to the coefficients for heat and mass transfer. And overall, being familiar with these processes is becoming more and more relevant as the industry and demand grows. So it's important for us as future engineers to approach new subjects like this as a challenge to try and see what kind of new information we can discover.